In this video, we are going to go through the final exam review and methods at which to find the solutions. So we'll start with question one. We given a function f of x, and we're asked to answer the following questions. In part A, they're asking us to evaluate what f of -2 is. And so I would start this by just plugging in -2 everywhere there is an x, just like so. And next, we just want to simplify the right-hand side of this equation. So we see that we have -3 times 4 minus 10 is equal -12 minus 10, and finally -22. Moving on to part B, we're asked to solve f of x when it's equal to 2. So I'll start by just saying -3x squared plus 5x, which was our f of x function above. And we're going to set this equal to 2. To solve this, we're going to subtract 2 from both sides of the equation and find that -3x squared plus 5x minus 2 is equal to 0. To solve this, you can do a few different things. We can use the quadratic formula. We can use methods of factoring and apply the zero product rule. I'm going to go ahead and use factoring to our benefit and use the zero product rule. But first, I will go ahead and just multiply both sides of the equation by -1, which will just flip the signs for each one of the terms. So I'll have 3x squared minus 5x plus 2. And of course, -1 times 0 is just 0. So it's all equal to 0. Next, I'll go ahead and use the AC method. And so I see that my 3 is the leading coefficient, A, and 2 is my C value. Of course, those multiplied together equal 6. And the two factors that when multiplied together equal 6, but when added together equal -5 are -2 and -3. So we'll go ahead and rewrite our equation. And instead of writing -5, we'll write -3x minus 2x. And then, of course, plus 2 equals 0. Next, we're just going to factor by grouping and pull out the greatest common factor out of the first two terms, which is 3x, relieving x minus 1. Next, the next two terms, or the last two terms, the greatest common factor, it'll be beneficial if we factor out a -2 here, and then we get an x minus 1 again, which is perfect. Now, finally, factoring out that x minus 1, we have this is all equal to 0. So the zero product rule tells us that if these two factors multiplied together equals 0, then it must be that 3x minus 2 is equal to 0, or that x minus 1 is equal to 0. And if we solve either one or both of these, I should say, for x, we'll find that 3x is equal to 2, and finally, x is equal to 2 over 3. And the same can be done when x minus 1 is equal to 0. We see that, of course, this implies that x is equal to 1. And moving on now for part C, we're asked to find the zeros of the function f of x. And again, f of x is equal to -3x squared plus 5x. Finding the zeros means let's go ahead and set this equal to 0 and solve for the x values here. So here we can actually just start by factoring out an x out of both of these terms. And that leaves a -3x plus 5 equals 0. The zero product rule, of course, again, can be applied here. And we see that either x is equal to 0 or -3x plus 5 is equal to 0. So solving the right-hand side equation, we see that This implies that negative 3x is equal negative 5, or rather, x is equal to 5 over 3. So the zeros here are x equaling 0 and x equaling 5 over 3. And we can move on to part D, and they tell us to state the x-intercepts as ordered pairs. So I like to always remember that if I'm on the x-axis and intercepting it, my y value or my f of x value must equal 0. So really they're asking us, well, when is f of x equal to 0? And so this should seem familiar. This is what we just did in part C. And they just want us now to state that information as an ordered pair. So we know the x values from above, 0, and the other ordered pair has an x value of 5 over 3. And again, that scenario is those f of x values or those y values as an output should be equal to 0 if we're hanging out on the x-axis. Perfect. Okay. Next, we're asked to find the y-intercepts and write it as an ordered pair. So kind of using the same method that we just applied in part D, the observation here is that the x value, if we're on the y-intercept, is equal, or sorry, if we're on the y-axis, is equal to 0. So this in turn is basically asking us to say, what is f of 0 equal to, right? And so we know that the function f of x, that is just equal to negative 3x squared. So I'm going to go ahead and plug in 0 plus 5 times x. And again, I'm plugging in 0 wherever there's an x. And we see, well, if we went ahead and solved or simplified this, we would find that we would have 0 plus 0, which in turn, of course, is just equal to 0. So the y-intercept, the x value is 0, and we just observed that the output is also equal 0. So the origin is the y-intercept here. Okay, moving on to the last question. For question number 1, they're asking about the in behavior here. And so we should recognize that this function f of x is our friend, the parabola, since it's a second degree polynomial. And we know the behaviors of these, right? They're either going to be, as we say, concave down or concave up. And we like to look to the sign of the leading coefficient to determine this information of which one this is. And since we have a negative sign as the leading coefficient shows here, this implies that we have concave down. So this scenario here. So we could say, well, as x goes off to negative infinity, f of x, or the outputs, go to negative infinity as well. And then as x goes off to positive infinity, the output f of x goes off to positive, oh, sorry, my apologies, negative infinity. Okay, moving on to question 2 here. Now they're giving us a function g of x. And right away, they're hitting us with stating the in behavior here. And so we will first note that g of x has odd degree, and also that the leading coefficient is positive 2. So we see then that implies that as x goes to positive infinity, f of x, the output, also goes to positive infinity. And as x goes off to negative infinity, this implies that f of x goes off to negative infinity. So again, that was just based off of the fact that we have an odd degree polynomial. and the leading coefficient is positive. So it's kind of the iconic shape, kind of like this. Moving on to part B here, they're asking us to state the vertical intercepts as an ordered pair. So the vertical intercepts, we might read that as the y-intercept. And again, like we did in question one method to observe this is to say, well, if I'm on the y-axis, my x must be equal 0. And so here, this is just a process of saying, well, what is g of 0 equal to? And so you can see from above, there is an x in each one of these terms. And anytime we multiply by 0, whether that's 0 times 0 and then times a number 11, for example, that's always going to be just equals 0. So we see here that the vertical intercept, the x value is 0, and the output, as we just observed, is also equals 0. So we're at the origin again for the y-intercept. Next, in part C, they're asking us to find the zeros and state if they are cross or touch points. So let's look up here what g of x was again. G of x is equal to 2x cubed minus 11x squared plus 5x. And to find the zeros, we're going to go ahead and set g of x equal to 0 and solve for those x values, just like so. So to start, we can see what the GCF is in all of these terms. Unfortunately, 2, 11, and 5 are all prime numbers, and so there is no common factor other than 1. But we do have a variable x in every single one of these terms, and so I'll start by factoring out an x. Make a nicer x there. Try to. Okay, and so what remains after I factor out an x? Out of the first term, we have 2x squared minus 11x, and then, of course, plus 5 at the end here, all equal to 0. So let's see, what can we do here next? We might, if we wanted, we could use, say, for example, the quadratic formula, if you'd like. I'm going to go ahead and just show the factoring method again. And since the leading coefficient of this stuff inside the parentheses here is greater than 1, it's 2. I'm going to use the AC method. So I'll say, well, 2 times 5, or A times C, is equal to 10. And I'm just going to think about what are the factors of 10 that add up to equal negative 11. And let's see, that would be negative 10 and a negative 1, if I'm not mistaken. So I'll go ahead and rewrite what we have above. But instead of writing a negative 11x, I'm going to write, let's try negative 10x minus 1x plus 5. Have that equal to 0 still. Again, we can go ahead and think about the first two terms on the inside of the parenthesis and what the GCF is here. I believe it to be 2x, which would leave, let's see, an x minus 5, I believe. And next, I think it'd be advantageous of us. We have a 1 and a 5 in the next two terms, which are, of course, probably want to factor out a negative 1 here. Let's try that. And that would leave an x minus 5, which is perfect. I believe that's what we were after. So now we can finally factor out the x minus 5. And we'll find that we have x times 2x minus 1 times x minus 5. All of this is equal to 0. And here we can just happily apply the 0 product rule. So we find that x is equal to 0, or 2x minus 1 is equal to 0, which implies that x is equal to 1/2. or x minus 5 is equal to 0, which implies that x is equal 5. So they're saying find the zeros and state if they cross or are touch points. So our zeros are x equaling 0, x equaling 1/2, and x equaling 5. And I believe we would look here at this factored form of our equation and note that none of these factors are being squared or cubed. In fact, they are all being raised to the power of 1. Therefore, all of these zeros are cross points. Okay, next we are asked to sketch the graph of g of x. And so we'll use the information we have gathered for the first few parts for this. All right, let's start. I'll go ahead and draw my, try my best to draw my x and y coordinate system, like so. And maybe I'll, instead of writing y up here, right, we're dealing with a function g of x. And we know that the y-intercept is here at the origin. And we saw that the x-intercepts, of course, x equaling 0. Let's go ahead and just mark this and say this is 1/2, right? And I would say that this is approximately about 5. You want to probably add some tick marks here as well for more information. And so let's see, I believe we talked about maybe we didn't on this one. We did. We talked about the end behavior in part A, if you recall. And we kind of saw it potentially as this kind of behavior here. So we can put all of this together, right? We know that initially the function must be coming from down below, like so. And I'll add an arrow here. And we know it must turn and intercept the x-axis at x equaling 1/2, as we observed in part C. And then the function must come out, and since it intercepts the x-axis, it must come back, intercepts at x equaling 5, and then the end behavior goes off to infinity, like so. So that's a rough sketch of what the function g of x looks like, based off all the information we gathered. Right, moving on to question 3. They give us a function f shown below, and we're asked to use it to find all the zeros, including the complex zeros. Okay, so right away, they actually give us a 0 on this just by observing it on the graph itself, right? It's here at x equaling -2, and the output, of course, since we're on the x-axis, is equal to 0. So this implies, let me go to my notes here, right? This implies that, of course, x equaling -2 is a 0. So in this world, right, if we were writing this as a factored form, there must be an x plus 2 factor, right? Let's see. Okay, they're calling this f of x. So we say f of x, right, must have this factor x plus 2. And then hopefully there's going to be some other factors here, right? And in fact, we know that there is a potential for 3 zeros, right? Since this is a third degree. So we want to see what these two factors are, right? Okay, and so we can go ahead and do this in 2 different ways. These are my ideas of a method for solution. We can use long division, and I'll go ahead and show that method first. And then we can also use synthetic division, and I'll show that second. So here we can go ahead and factor out the factor of x plus 2 out of our original function, x cubed, make sure I get this right, minus 4x squared, oops, minus 2x, that 2 doesn't look that happy, plus 20. Let me finish my division symbol here. Okay, so I like to think about it in terms of what number times x, or what term times x equals x cubed. And I believe that will be an x squared. And so when I multiply x squared by x plus 2, I will get an x cubed plus 2x squared. Go ahead and subtract that value. And we'll find that we'll have a negative 4x because the x cubes subtract each other and get 0. We'll get negative 4x squared minus 2x squared, get a negative 6x squared. And I'll go ahead and bring down the next term, minus 2x. Okay, that was the end of the first part of the algorithm. And now we just go ahead and repeat the process. What times x is equal to negative x squared, which of course is minus 6x. All right, and now multiplying that over, I'll see that I get negative 6x squared minus 12x, which I believe is correct. Go ahead and subtract these two. Of course, again, we have negative x squared plus 6x squared. That's perfect. That's what I want, which is equal to 0. And then I have negative 2x minus a negative 12x, which of course is negative 2x plus 12x, which will be 10x. And then I'll go ahead and bring down the last term, and that ends our second run through of the algorithm for dividing. Okay, and now we'll think about one last time, what times x is equal to 10x? And we should find that that's equal to positive 10. Make my plus sign a little bit nicer there. So 10 times x plus 2 gives me 10x plus 20. Go ahead and subtract these. Of course, this is equal 0, which is what we were after, right? We knew that x plus 2 did divide this function, f of x. So we have found, I'm going to go ahead and write it down here, that the remainder, after I go ahead and divide out the x plus 2, is equal to x squared minus 6x plus 10. Okay, and that was the long division method. And I'm going to go ahead and want to set that equal to 0 and solve for the x values. But before we do that, let's go ahead and just run through synthetic division. This one won't take as long, but we'll go ahead and set up the process. So I like to do my my synthetic division like this, and putting the coefficients of the original function f above. So x cubed's coefficient was 1, for example, and then I had a negative 4, a negative 2, and then 20. Okay, and so we saw that negative 2 was a 0, so I'm going to go ahead and we're going to use the negative 2 here, bringing down the 1 down below, and do negative 2 times 1, which is negative 2, negative 4. Adding the negative 2 is equal negative 6. Negative 2 times negative 6 is positive 12. Negative 2 plus 12 is negative 10. Oop, my apologies. Negative 2 plus 12 is positive 10. And then finally, negative 2 times 10 is negative 20, which combining those, we'll get our 0. That's what we were after, of course. And so here we see that this is now, since we started with this being our coefficient of x cubed, x squared, x, and our constant, we now have our coefficient for x squared, x, and our constant here. So of course we see that we have x squared minus 6x plus 10, which is what we found with the long division as well. Perfect. So moving on, right, we see this second degree polynomial we're trying to solve, or set equal to 0 and solve for the x value. I'm going to go ahead and use the quadratic formula here, right, where let's go ahead, I'll label my A, my B, and my C. And going ahead and saying that I can plug this into the quadratic formula, doing negative b, or -6, plus or minus the square root of b squared minus 4 times my a value times my c value. Finish my square root symbol. All of this will be divided by 2 times a. Perfect. Okay, let's go ahead and start our simplification process. We know -6 is obviously +6. The square of -6, right, or -6 squared is equal 36. 4 times 1 times 10 is equal 40. 2 times 1 is just equal 2. Okay, so we have 6 plus or minus 36 minus 40 is -4. So we have the square root of a negative value. And we can go ahead and say right away, then our imaginary number I is coming into play. And so we have the square root of 4 times I is one way of writing this, divided by 2. And let's go ahead and just write it to the right here. We can see that we can split this fraction up and have 6 divided by 2, which is equal 3, plus or minus the square root of 4 is equal to 2. And dividing that by 2 is equal to 1. So we just have 3 plus or minus our I. And did I forget some things here? This looks good. Okay. And so let's go ahead and state the information we have and remember what they were trying to ask us here. Okay, we want to find all of the zeros, including the complex zeros. And so we'll go ahead and label these, right? We know that it was given that x equaling -2 was one of those zeros. And then we saw through our process just now that 3 plus I is a 0 and 3 minus I is also a 0. Perfect. And those are the zeros. That's our final solution. Moving on to question 4, they're asking us to determine the equation of a 4th degree polynomial function with the following characteristics. Right away, they give us that 1 and -2 zeros with multiplicity of 1, right? So let's see, that implies that x minus 1 is a factor and x plus 2 is a factor. Okay. Next, they tell us that 4 is a 0 with multiplicity of 2. So again, kind of the same process we just did, right? We say, all right, that implies that x minus 4 is a factor. And since it says multiplicity of 2, we know that implies that there's a 2 in the exponent position for this factor. Okay, so moving on, they say, well, the graph goes through the point 3, -1. So at this point, we know, right, this is a 4th degree polynomial. So we have actually described all of the factors, and we can put that together. I'm going to go ahead and just label this f. So I know then that f of x is equal to x minus 1, x plus 2. Those were the first 2 factors that we observed. And then the last bit of information was that x minus 4 squared are the last 2 factors. And what I like to label here is I just put an a value in front for just some constant coefficient. And we'll go ahead now. We have this kind of laid out for our benefit. We can plug in this point here, right? When we plug in 3 into this equation, this output should equal -1. And so I'm going to go ahead and just say, well, -1 must then be equal to plug in 3 wherever there's an x. And then I'll go ahead and just simplify and solve for my a value here. So let's see, I know then that 3 minus 1 is equal to 3 plus 2 is equal 5. And 3 minus 4 is equal to -1, but -1 times -1, that is -1 squared, is equal to just +1. If we multiply these three numbers together, we get that it's a times 10 is equal to -1. And of course, if we solve for a by dividing by 10 on both sides, we get that a must be equal to -1/10. Therefore, this implies that our function that I've decided to call f of x must be equal to -1/10 times x minus 1 times x plus 2 times x minus 4 squared. Moving on to question 5, they ask us to kind of repeat the process, but this time we have a rational function and we have different characteristics. Okay, so right away they hit us with the information that the domain is such, and also that we have vertical asymptotes at x equaling 2 and x equaling 4. I always like to think about vertical asymptotes as problems in the domain, so I like to use this bit of information at the same time. So this implies, right, that our denominator must then, let's call this, maybe I'll call it g of x, right? G of x's denominator must have factors of x minus 2 and x minus 4, right? Because I can't divide by 0. That means I'm not going to be able to plug in 2 or 4, which makes sense with that above information. Next, it's giving me information about the horizontal asymptote at y equaling 0. And so the horizontal asymptote at y equaling 0, it implies that the degree of the numerator is less than the denominator. And we just saw that the denominator, we can kind of infer from this information that I just wrote down about the denominator, that it has degree 2. Thus, the numerator's degree is going to be either 0 or 1. So maybe I'll write down numerator's degree must be less than 2, right? So it's either 0 or 1. Okay, moving on. It says there are no x-intercepts. And so since there's no x-intercepts, this implies that the numerator is constant. That is, there's no x variable in the top of our fraction, right? So let's see what that could look like. I would say my function, like I was saying, I'll call this one g of x for no reason other than just to have a label for it. And we know that the denominator is going to have these factors stated above. And I'll probably just go ahead and reuse my a variable for representing the constant. And this definitely agrees with what we just said about the numerator having degree 0 or 1. Here, the numerator has degree 0. So that's perfect. Okay, so next, they give us this kind of familiar point that this function g of x must pass through this point. So therefore, I'm going to go ahead and just say, well, anytime I plug in 3 into this function, the output must be -1. So I'll go ahead and plug in 3 wherever there's an x. And then that's supposed to be an a. It kind of looks like a 9. So I'm going to go ahead and simplify and solve for a now. Right away, I can see, okay, 3 minus 2, that's equal 1. And 3 minus 4 is equal to -1. So I have a positive 1 and a -1 in the denominator. Multiplying those together just equals -1. And this, of course, looks like it's going to say that -1 is equal to a divided by -1. I could do a few different things. One thing is you could just multiply by -1 on both sides. And you see that this implies that a is equal 1. Perfect. So if we wanted to, we can just hand the reader the final result that g of x is equal to 1. That was our a value we just found, over x minus 2 and x minus 4. Perfect. Okay, let's move on to question 6. In question 6, they give us a function c of x, which is a rational equation. And they're asking us to find the y-intercept and state it as an ordered pair. So again, if I'm on the y-axis, my x must be equal to 0. So I'll go ahead and just start by plugging in 0 into my equation. Find 0 minus 1 and 0 plus 4 is in the denominator. And simplifying this, I see this must just be equal to -1 over 4. And stating this as an ordered pair, we saw if I plugged in 0 for my x value, the output was -1 over 4. Next, in part B, they're asking us to find the x-intercept and state it as an ordered pair. So again, this implies if I'm on the x-axis, my y is equal to 0. So we run into setting this equation c of x, which is x minus 1 over x plus 4, equal to 0. And if we have a rational equation that's equal to 0, this implies that the numerator must be equal 0, or x minus 1 must be equal to 0. In turn, we see, of course, that x equaling 1 gives us that 0. So we can write this as an ordered pair, right? We said that x equaling 1 must give us an output of 0. So 1 comma 0 is our ordered pair. Okay, and so moving on to question C, they're asking us for a vertical asymptote. And so vertical asymptotes, that's where the denominator is equal to 0. So very similar to part B, but now we're going to set the denominator equal to 0. So x plus 4 equaling 0 implies that x equaling 0 is our vertical asymptote. Perfect. Okay, now to find the horizontal asymptote. Note here with x minus 4 over x plus 4, the degree of the numerator is equal to the degree of the denominator. So the horizontal asymptote is actually just the ratio of the leading coefficients, which in this situation actually just equals 1 over 1. So our horizontal asymptote is actually just at y equaling 1. And here they're telling us, or asking us, I should say, graph the function by drawing the asymptotes and the intercepts, then evaluate a few additional x values as needed and plot these ordered pairs. Finally, sketch a smooth curve. So this will be a few step process. Let's go ahead and start just with our x and y coordinate system. And I think I called this g of x. So maybe I'll put a g of x. Oh, no, sorry, this was c of x. C of x. Okay, so they say draw the asymptotes and the intercepts. Okay, and so we had a vertical asymptote at x equaling -4. Okay, so I'm going to go ahead and just choose this to be my -4 out here. Okay, maybe I'll label it as well, x equaling -4. And let's see, the next one is the horizontal asymptote. And we found that to be actually just the ratio of the leading coefficients, which was y equaling 1, or c of x equaling 1, I should say. Let's go ahead and put that one about here, roughly. And I'll say, okay, this is where c of x is equal to 1. And let's see what's next. We want to talk about the intercepts, right? Did we find the intercepts for this one? Let's see. We did. We found the y-intercept to equal 0, comma, -1/4, and the x-intercept to be 1, comma, 0. Okay, so 0, comma, -1/4. I'm going to be on the y-axis for this one. And let's go ahead. Maybe I'll choose a different color so it stands out a little bit more. So I think it's probably going to be right about there. Maybe use your best judgment there. -1/4. I'll label it. And then the x-intercept, I kind of ran out of space here, but I think it's probably going to be about right there, right? And I'll try to label this one as well. I think the graph will probably run into this. It's 1, comma, 0. And then let's go ahead and there's also saying, let's maybe put in a few additional x values, right? So maybe I'll just write a table real fast just to collect that information. And if we remember, right, our c of x function is equal to x minus 1 over x plus 4. So you can try to choose some advantageous x values to get nice results if you can. So x equaling -5. I think that one turns out pretty nice. Would have -5 minus 1 over -5 plus 4. And I think if I remember correctly, this should be equal 6. So this one's good, right? Because we had 2 points on the right side, right bottom side of all of these asymptotes. But this point, right, it's going to be maybe, let me choose my green color again. It's going to be maybe somewhere, do my best here, maybe right around here at x equaling -5 and the output equaling 6. So let's go ahead and try to draw the curve here, right? So we know it's going to intercept here and probably proceed towards this x, sorry, this vertical asymptote in this way, and also proceed towards the horizontal asymptote in this way. And the same could be said up here, knowing we got to touch this point, -5, +6. And so that would be a nice way of drawing it. And we could, of course, take a little bit more time and evaluate more values, right, to really confirm this information. We'll go ahead and stop there for now. Okay, let me get back to my black. And they're asking us to, in question 7, they say, well, let f of x equal this function and g of x equal this function, and find and simplify the following. Okay, so here they're asking us in part A to take the f function minus the g function when we evaluate a into it. And so I like to go ahead and just start by writing this implies f minus g of a is equal to f of a minus g of a, which we can see above that this is equal to a when evaluated into f of x which is this. And let me go ahead and label this part A. And now we're going to subtract g of a, right? And here I think I would suggest using parentheses, right? To make sure I don't mess up any signs at all. When I plug in a into g, I get negative a minus 2. And in this next step, I can go ahead and break down the parentheses. So we would have, of course, just negative 3a squared plus 5a. And then here, if I distribute the negative inside the parentheses, we would get plus a plus 2. Combining like terms, I get negative 3a squared plus 6a plus 2. Okay, and that would be, I think, as simplified as it can be. Let's go ahead and move on to B. I'm going to go ahead and label B. And here it's saying, it says this fog notation is how I've heard it pronounced in the past. But this is the composition of functions, and that we would say, okay, well, B is asking us to find f evaluated at g of 3. I can make a better 3 there. And so we just go to the above information. I'm going to do it in my own way. You can do this however you choose, but the important part is to kind of stick to one method and make sure that you keep things straight. And so g of 3 would be negative 3 minus 2, right? And let's see, we can go ahead and simplify that. Negative 3 minus 2 is equal to what, negative 5. And so now we're just landing on, well, what is the f function evaluated at negative 5? So let's go ahead and see what that looks like. Plugging in negative 5 to everywhere there's an x. Okay, so we have our work cut out for us here. Negative 5 squared is equal to 25. So we have negative 3 times 25. And here, 5 times negative 5 is minus 25. Cool. So we see negative 3 times 25. That's equal to negative 75. Actually, I'll go ahead and put the result over here. So again, we had negative 75 minus 25. And it's just negative 100. Perfect. Okay, so I think I left a little room here for part C. Part C actually is just nice enough to hand us this, right? G of f of a, right? So we're going to go ahead and start with the inside. What is f of a? So f of a is just plugging in a wherever there is an x. Make that a little nicer. So negative 3a squared plus 5a. And now we're going to go ahead and take that expression and plug it into our function g, wherever there's an x. And I'm going to go ahead and first just use parentheses and say, plug in negative 3a squared plus 5a, where that x was, and g. And then don't forget that minus 2. Okay, so now I can distribute the negative that's in front here. It's supposed to be an arrow in front of our parentheses. And so I'll get 3a squared minus 5a minus 2 as our final result. Perfect. Okay, that's question 7. Moving on to question A, they ask us to use the composition of functions to verify that the functions are inverses of each other. So here we can go ahead and do something similar that we did in question 7 and just say, well, what is f of g of x equal to? The composition. And let's go ahead and find out here. So I'm going to take whatever g was, right, which is stated, and plug it in to f. So 3, and parentheses are your friend here. plus 2. Okay. And then the f function tells me to subtract 2 now. Okay, so going ahead and simplifying this, right? We see that 3 multiplied in would be 3 times -1/3. That would simplify to just -1. Then my x plus 2, and then -2 on the outside. So here, distributing the -1 into my parentheses, I would find that I'd have -x minus 2 minus 2. Of course, we see this to be -x minus 4, which of course we want this to equal x. It does not. Therefore, we observed already in part A, f and g are not inverses. Okay, next for part B, let me go ahead and make sure I label this A. I think it's assumed this is also part B then. I'm going to do the same process by first just plugging in g of x into my function f. Here, let's make sure I keep this straight, right? Everywhere there is an x in my function f, I'm going to plug in the function g. So I have, instead of x, I'll plug in g, which is 2 plus the cube root x minus 2. All of this is cubed. I can combine the 2 and with the minus 2, that of course equals 0. So I'm left with 3, the third root, I'm sorry, of x raised to the power of 3. And, one way we could look at this is as a rational exponent. We have x to the 1/3 cubed, which of course is just equal x to the 1 or x, which is perfect. Okay, so it passes the first test. Next, we want to go ahead and double check. If I plug in f into the function g, will we get the same result? The output is x. So our g function is 2 plus the cube root of x, which here I'm going to go ahead and plug in x minus 2 cubed. Again, for a similar reason, we can see that the cube root undoes the cube, and we'll have 2 plus x minus 2, which again nicely simplifies to just x. So perfect. We see now that in part B, f and g are inverses of each other. Moving on to question 9. Question 9, they're asking us to state the domain in part A. And so here, let's see, the domain, of course, is just going to be equal to all the x values, right, that are usable in this function. And making sure, okay, we don't write down if there's any holes or anything like that in the domain we concern ourselves with. And then, of course, as asymptotes as well. And so here we can see that there is this vertical asymptote. So we're going to have to take that into account for our domain. And so we could write this in a few different ways. Maybe I would start by just saying, I think I left space down below here. So for part A, right, we see there's an asymptote at x equaling positive 4, right? Let's see, x equaling positive 4. And this information could be written on a number line if you need, or we could just go straight to interval notation. And so we can assume that x can go off towards -infinity just fine. There's no other issues that we can see from the graph. And it can get as close as we want to 4 from the left-hand side, but never equaling 4. And then we'll go ahead and use the union symbol. right? And the same concept here, it can get as close as we want to 4 from the right-hand side now, but never equaling 4. And then it looks like it can just go off to positive infinity just fine. So this would be the domain. I'll just label it the D. Here for the range, there are no horizontal asymptotes that I see. However, I am seeing that y cannot equal -1. It doesn't appear to me on this function, right? Since I have a hole here, and of course the hole here. It looks like to me that we can't have y equaling -1. That's not a possibility. So in a very similar fashion from before, right, where I said, well, x equaling 4 is a vertical asymptote, or that x can't equal -4, and the domain followed. Here, I believe, right, that y cannot equal -1. And therefore, if I'm defining the range in this interval notation, I see that I'm assuming that it can go off to -infinity just fine and get as close as I want on the left side to -1, never equal it, and the same on the right side, and go off to infinity just fine for the range. Next, we are going to have part C, and part C is asking us to find f of -3. So we're just going to go ahead and plug in x equaling -3, right? Let me go ahead and erase this little line here. So when x is equal to -3, right? So here, we look at the output, and the output looks to me to be 3. So when x is equal to -3, the output is +3. All right, so last question here is asking us for what values of x does f of x equal to? So what x value are we plugging in order for the output to be equal to? And so here, probably best to just go to y equaling 2, right? Which is here, right? And we see, okay, the function looks like it intercepts y equaling 2 here, here, and here. And so this would just be our list of x values, right? We see x equaling -4 is one of those, -2, sorry, apologies, -1, I should say, and +1. So for part D, the x values that give us f of x equaling 2, again, are x equaling -4, -1, and +1. Perfect. Moving on to question 10. They ask us, or they tell us the graph of y is shown, and they want us to sketch y equaling -f of x plus 2, and then subtract 1 on the x. Sorry, subtract 1 on the outside, and we're going to plot it on this same axis down below. And show your work either by showing the transformations of key coordinate pairs or stating the transformations needed in the correct order. And so the transformations kind of follow, they do follow the order of operations that we're accustomed to. And so we can take each one of these points one by one and just show that it follows the order of operations. So we know first we are going to add 2, right? Because that's on the inside of the parentheses. Then we're going to multiply, right? Multiply by -1, right? That's the coefficient out here. And then finally, we're going to subtract 1. Okay, so yeah, let's see how this looks, right? Adding 2 on the inside of the parentheses will move this to the left 2. Multiplying by -1 is going to reflect across, let me spell that right, across the, which axis? The x-axis, right? Okay. And then subtracting 1 is the nice one, just moves down 1 unit. Okay, so let's see. Our point here, the y-intercept, -1 is the output. And so if I go ahead and add 2, which would be moving it to the left 2, I would be moving it here. And then reflect it across the x-axis. So I'm going to move it up here. And then now I'm going to move it down 1. All right, moving it down 1. Let me go ahead and change my color because this will be the final place. It's got to be right here, down 1. Okay, perfect. Okay, so my next point I'm going to worry about here is the point 3, 2. So 3, 2 is going to move to the left 2, reflect across the x-axis. So it'll move down here. And then the final place for it, right, will be down 1. So we're going to land on, looks like, let me choose a different color here that stands out a little bit more. The x is 1 and the y is -3. Okay, so again, repeating the process, left 2, reflect across the y-axis, and then down 1. Okay, left 2, reflecting across the y-axis actually just keeps it on the, sorry, reflecting across the x-axis, keeps it on the x-axis, and then down 1. So we have our point here. Okay, and so now we can connect these dots. Right, I'll do my best to draw a straight line. Connecting these dots. And we see our final result. Perfect. All right. Let's go ahead and scroll down to question 11. Question 11 asks us to write the equation of a function whose graph is y is equal to x squared, but is transformed in these individual ways below. So shifting to the right 2 units, right, implies, right, I'm going to call this my g of x function. We know that this will shift to the right 2. It's going to be adding, no, I'm sorry, subtracting 2, right? That's the one we have to remember on the inside of the parentheses. So I'll go ahead and write x minus 2 on the inside the parentheses, less like that. Okay, shifted down 2 units. This one's a little bit friendlier, right? This new function g of x is equal to f of x, right? Down 2 units, just subtract 2 on the outside. This is equal x squared minus 2, just like that. Part C asks us to reflect over the y-axis. Okay, so reflecting over the y-axis, right? That's going to mean that we want to multiply the x by -1. So this new function g of x is going to be equal to f of -x, right? Which is equal to -x squared. And if you wanted to, you could see -x squared is -x times -x, which is just positive x squared. In part D, they're asking us to reflect over the x-axis. So this new function g, right, will be negative f of x. Multiply the function, the output, by -1. This one's just negative x squared, just like that. Okay, finally, they're saying the vertically stretched by a factor of 3, this new function g will be 3 on the outside of our function being multiplied like that, 3 of f of x, or 3 times f of x, I should say. And this, of course, is 3x squared. Perfect. Moving on to question 12, we have our first story problem. And you, of course, read it over. And they're asking us to evaluate L of 10 and explain its meaning in the context for part A. And of course, always including the units. So here, I'm going to go ahead and just plug in 10 wherever there's a t in our equation, just like so. And the results here, right, I would say that's equal to 12.5 plus 61, which is equal to 73.5, right? And the units are liters. And so you might say something to the effect of, after 10 minutes, right? Because t was equal to 10. There will be 73. There will be, just trying to write this fast here, will be 73.5 liters of liquid, right? Of liquid, spell quickly, in the tank. One potential answer. Okay, so for part B, they're asking us to find the inverse function here. My method of finding the inverse is as follows. I start by just saying, instead of L of t, I'm just going to write it as y is equal to 1.25 t. Maybe I'll write x, actually. Let's go ahead and just change that to x. That might be advantageous for us in the end, and you'll see why. So again, just changing L of t and t to y and x. Finish writing the equation. And now it kind of feels funny, but we're going to go ahead and just switch these variables around, just like so. 61. And now go ahead and just solve for y. And so I think we'll find that y is equal to x minus 61 over 1.25. And this is now our inverse. So we can go ahead and write L inverse. And this is why I was suggesting x be changed from t. This is equal to x minus 61 divided by 1.25. I dropped my 1 there. Perfect. That's the inverse, where x is the output of the original function L. Okay, so now they're in part C, they're asking us to use this inverse, right? And plug in 76. So this is equal to 76 minus 61 divided by 1.25. Okay, I can do the 76 minus 61 in my head fairly easy. It's equal 15. I might grab a calculator for the next part here. 15 divided by 1.25, I think happens to be 12. So here you can say this in a few different ways. My brain initially said it'll take 12 minutes for the tank to reach 76 liters. That's how I was thinking about this. You could also say if the tank has 76 liters, then it has been filling for 12 minutes. And of course, here in that statement, you always make sure that you include the units. Okay, so moving on to question 13. They're asking us to find an exponential equation that fits the given points. So let me check my notes here, make sure I'm staying on path here. So an exponential equation, I'll probably just start by stating what that looks like in general form. Y equaling a times some base value raised to the x value, right? Okay, so now I have kind of a guide for the next few steps. And it's advantageous for you to pick on the middle point first. So this guy here, right? Because the x value is 0. So this is going to help us, right? We're going to use an important property here of raising something to the power of 0. And so we see that y is equal to a times b to the 0. And actually, I should say that this is equal 5, right? Because I plugged in my x value. So 5 is equal to a times b to the 0. And we know that b to the 0 is just equal 1, right? Doesn't matter what b is. And then this, of course, implies that a is equal to 5. So perfect. We can go ahead and update our equation now. We see that, let's say, a is equal to 5. B is still unknown, right? That's supposed to be a B, not to mistake this as 56. Don't know if I did much better there. So the next one that I chose to use was the point -2, 125, the first point given. So the output is equal to 125, and the input is -2. So this guy implies, right, getting rid of that negative exponent might be your first step. And then going ahead, maybe I'll multiply both sides by b squared. And so I'll get 125 b squared is equal 5. And then dividing both sides by the 125 to get b squared by himself, I get 5 over 125, which, 5 and 125, they have a greatest common factor of 5. Let's see, I think that's 1 over 25. And we can go ahead and take the square root of both sides to see what b is equal to. And so I know that 1, the square root of that is equal 1. Square root of 25 is equal 5. So I think I have plus or minus 1 over 5. But if you remember in this exponential equation or this form, we always assume that b is greater than 0. So in this one, we're just going to go ahead and say b is equal to 1 over 5. And so our final equation is just equal to, let's see, a was 5, and my b is 1 over 5 raised to the power of x. And if you want, you can go ahead and use the third point to check your work. That would be a good idea on the exam if you had time. Okay, and question 14, it's giving us another word problem, the fox population in a certain region. And I'll let you read the rest. Okay, and so in part A, they're asking us to write the first 4 ordered pairs, assuming that t equaling 0 is the year 2012. And so it might be helpful to begin just to state what kind of equation we're going to be using here. So this is the form that I have it in, right? A is equal to P, times 1 plus R, which is my rate, raised to the power of T. My independent variable here is time. And obviously my principal value or my starting value is equal to 23,900 foxes. My rate, they give it to me in a percent, right? I can divide by 100 to find that this is 0.09 as my R value. And so in this scenario, I believe I've already worked a bit further on, and that we'll see that this will come in handy, I believe, in part B. But we can go ahead and state, right, plugging in the first few values for t, starting with t equaling 0, right? And so if I wanted to, I'll plug in t equaling 0 and this equation. So let's see, 23,900, 1 plus 0.09 or just 1.09 raised to the power of 0. is equal to, with this exponent of 0, we'll just get 23,900. And so here the ordered pair is 0, comma, 23,900. Okay, moving on. We'll do the same method, but we're going to go ahead and plug in 1, right? And if I use my calculator, I believe it comes out to a nice even integer, and it's 26,051. So again, that ordered pair is 1, comma, 26,051. Moving on to year 2, right? Year 2, we'll plug in a 2 for our exponent. And I think here, so we had to be, I'll do a little extra work because our calculator is going to give us a number. Maybe it'll be something like 28,395.59. Of course, we want to talk about whole foxes. And so we'll probably round to the nearest integer value and find that in year 2, there'll be approximately 28,396 foxes. Finally, for our last ordered pair, let's go ahead and plug in the year 3. And your calculator, again, is going to give you a decimal value. Write out kind of what I've gotten. Right? Might be slightly different than your result. And the final order pair will be 3, comma, and I'm going to round that number to the nearest whole fox. Just like so. Okay. So moving on to part B, like I said, I think we did a little extra work in part A, at least the way that I went about it. And so we're asked to find an exponential equation, P of t, that models this data. The input should be t years after 2012, and the output should be the number of foxes. So I'll just go ahead and use this notation to what we were just doing, right? P of t, right? And we'll start with the initial number of foxes in 2012, which was 23,900. And then the rate again was 0.09. So I can write that as 1.09 and raised to the t. So here you might add, where t is the number of years since 2012 if you wanted. And P of t is the number of foxes after t years. Okay, and question C, they ask, well, what is the fox population predicted to be in the year 2020? And so I would probably start by just maybe if I had test brain, I would say, well, what is 2020 when 2012 is the starting year, right? A nice little easy calculation we can do in our heads, but it's nice to just show it on paper. Okay, that's what we did. Okay, so we have our equation. We just wrote it in part B. And I'm going to ask, well, what is P of 8 equal to? So we have 23,900, 1.09 raised to the power of 8. Okay. And so if you use your calculator is going to give you some decimal values. And so I'll go ahead and just write that, potentially what you're seeing on your calculator. 24714. And so with word problems or story problems, you typically will answer these in full sentences, right? So I would say something to the effect of, in 2020, the fox population is predicted to be or is, and I'm going to take that number we just found and just round it to the nearest whole number. So there you go. Moving on to question 15, another story problem. And so they're first asking us what the initial dose is. And so here, if we observe, they're asking, well, what is the dose when t is equal to 0, right? So we can go about it that way. We also know, looking at these for a while, right, you probably see that 25 would be the original dose, but we can show this, right, by just plugging in 0, right, into our equation. Oops. And, exponent of 0 gives us 1. So we get 25 times 1, or just 25. And so we want to make sure, of course, that we are using units. So this would be milligrams. Okay, and you can answer, of course, with a sentence if you wanted on that one as well. All right, part B is asking us what percent of the drug leaves the body each hour. And so this has to do with the rate, the R value, right? And so we saw that this equation in general, right, will be 1 plus R on the inside of the parentheses, right? And the inside of the parentheses here is equal to 0.85, right? And so here we see that R is equal to, let's see, I think that turns out to be a negative 0.15, right? Which we could translate to a percentage and say, that's negative 15%. But if somebody asked me what percent leaves, yeah, I'd probably say negative 15%, or I could say 15% leaves the body, however you choose to answer that. Part C, what is the amount of the drug left after 10 hours? So this just is requiring us to evaluate 10 into the equation given, just like so, because T is time in hours. And using your calculator, let's see, what did this one equal? I got kind of a long decimal, right? So I'll write maybe the first 2 digits. And then I could round this maybe to 1 decimal place. And so I would say something to the effect of there will be, right, 4.9 milligrams after 10 hours. Okay, part D, they're asking us to use algebra to find the number of hours, rounded to the nearest tenth of an hour, at which the body has 1 milligram left in the body. Okay, and so this one, right, knowing that our equation tells us the number of milligrams left, we are going to go ahead and set the equation itself, which was 25, 0.85 raised to t, the unknown time. This is all equal 1. So we want to solve for t. So right away, what I would do here is divide both sides by 25. And I see I get 0.85 raised to the power of t is equal to 1 over 25. Next, with the power of the logarithm, we can get to the exponent. And so I would probably just use the natural log. That's my preference. So I'm going to take the natural log of both sides of this equation. And that will bring down the exponent t to be the coefficient of this natural log of 0.85, which in turn has to be taking the natural log of the 1 over 25 as well. Okay, and so if we solve for t, we just have to divide by the natural log of 0.85. And so we see the final result here to be t equals the natural log of 1 over 25 divided by the natural log 0.85, which if you plug this into your calculator, I think it'll give you a number like 19, right now, 1 or 2 of these decimal places, something like this, right? So again, we want to answer these in complete sentences, and we'll say something like, it will take, right? And they told us in the problem statement to round to the nearest tenth of an hour. So I say, well, it'll take 19.8 hours. Perfect. Okay, question 16, it asks to explain how to find the domain of a logarithmic function. Explain how the vertical asymptote is related to this domain. Okay, and so the way that I would think about this problem is I kind of think about the general form for a second of a logarithm function. So maybe you have something written down or you've seen before that looks like this, right? And then vertical shift there. So here, if I were asked to find the domain in this general form, I would just find, right, when the argument of the logarithm, x plus c in this case, is greater than 0. So I would do something like to find the domain of the log function, set the argument, right? Set the argument greater than 0. So that might look like x plus c greater than 0. And then solve. Solve for x, right? So, and then solve for x. So we would say x is greater than negative c would be the domain. And then if we wanted to, we could go ahead and translate this to interval notation, right? Which I guess it's not necessarily asking us, but we could say, well, negative c up to infinity would be the domain. Okay, so next they're saying, well, explain how the vertical asymptote is related to the domain. So the vertical asymptote will be where the argument is equal to 0, right? So we'll say, okay, the vertical asymptote is related to the domain because it is the value x equaling negative c. You know, specifically the value that we said that x has to be greater than. Okay. In question 17, they ask us to sketch the function f of x, which is a logarithm function, right? And label 2 points and show any asymptotes as dotted lines, state the domain and range of the function. So kind of similar to things that we've seen thus far. First time we've seen a logarithm, of course, and we kind of are left on our own to figure out how to approach this problem. So the way that I thought about this first is I was thinking, I'll probably grab a table of values and use that to my benefit. So x and f of x. And so you can pick points that are favorable, right? Easy to calculate. So we know some rules here about logarithms, specifically that log base b or any value b of 1 is equal to 0. So here, my first value might be to try to make the argument equal to positive 1, which if I plug in negative 2, I would have negative 2 plus 3, which is equal 1. And so here, the output would be 0. So perfect. That's a nice one, right? The next property that I'll apply is log base b of b is equal to 1. So we have a log base 2. So I want the argument to be 2. So if I plug in x equaling negative 1 and add 3, that'll be 2, right? So log base 2 of 2, of course, is equal 1. So easy enough. Okay, so the next one is the idea that if I had some value, let's see, if I did this guy, right? B raised to some value, maybe I'll call it M, right? This is equal to, oh, let me write my M first, because we know that brings down the exponent. And we already saw that log base B of B is equal to 1, or just 1 times M, which is M. So it might not be perfectly clear what I'm talking about here, but what I want to do is to think about how do I create a favorable situation to use this property. And if I plug in x equaling 1, I'll get the argument to be 4, which of course is 2 squared. And then the result would be just the exponent of 2. Cool. Okay. Next, maybe we'll think about the asymptotes for a second. We were just talking about that, right? Asymptote. Should I spell that right? Asymptote. Okay. So the asymptote is where the argument is equal to 0, as we stated above. And so here, solving for x, we see that x equaling -3 is our asymptote. Okay, so let's go ahead and attempt to draw this guy. My x and y coordinate system. And we said, well, the asymptote is at x equaling -3. So I'll go ahead and put that down first, x equaling -3. And let's see, what else do we have here? We have our first point, which is at -2. And the output is 0. Okay, let me go ahead and signify that with another color. So right here, next point is at, let's see, x equaling -1, and the output is 1. So maybe I'll put that right about here. Make sure I label these, right? -1. This will be +1. And then the last point that we had was x equaling 1, and the output was 2. Okay, so somewhere right about there, right? And we're asked to go ahead and label 2 points on these, right? So here we've labeled 3, or put 3, and I can just label 2 of them, right? This is x equaling 1, y equaling 2. And then this point here is x equaling -2, y equaling 0. And then we know that it'll never equal the asymptote. So it's going to have some kind of smooth behavior. Let's do my best to draw our line like this. Perfect. Okay. Now they're asking us to state the domain and range, right? And so the domain, actually, we kind of already did this in one way or another, right? By talking about the asymptote. And so as we saw before, x plus b3 is the argument. We just set that greater than 0. And we find that the domain to start, right? We would say x is greater than -3, right? And in interval notation, this would imply that we could get as close as we want to -3 from the right-hand side and go off to positive infinity just fine. The range, as we see from our graph, right, can just freely go from -infinity all the way off to positive infinity just fine. Perfect. And that would be question 17. Moving on to question 18. We're asked to evaluate the following values of logarithms exactly. Okay, let's do these one by one, of course. So right away on this one, I would probably observe or want to observe that 9 is equal to 3 squared. And knowing I can bring down the exponent of this as a coefficient, that's a property of the logs. And of course, being that log base b of b is equal to 1, log 3 of 3 will be equal to 1. And then we would have 2 times 1, which is just equal to 2. For part B, this one's pretty easy, right? In some ways, right? Because we stated that log base b of 1, no matter what the base b is equal to 0. Okay, so for question C, we can start by bringing down the exponent like so. And we know that log base 5 of 5 is equal to 1, and 3 times 1 is equal to 3. Part D requires that we write well, at least this is how I thought of it, right? The cube root as a rational exponent. That was one of my first steps. And then I saw, okay, I can pull down the 1/3 out front of the log. And of course, log base 5 of 5, again, it's just equal 1. So we get 1/3. So this next one, this is how you might think of this, right? We can apply the subtraction property of logarithms, right? Since we have the division on the inside, or the argument, we can take the log of the numerator and subtract the log of the denominator, finding that log base 2 of 1 is equal to 0. And here we could write 8 as 2 cubed, right? 2 times 2 times 2 is equal 8. And so this will be -3. And then we'd have log base 2 of 2, which is just equal 1. So the final result should be -3. Okay, so for F, right? Remember we were talking about the fact that the argument, so if I just had the function log base 3 of x, I would tell you I would have to have the fact that x has to be greater than 0. And so we see, well, -3 is certainly not greater than 0. So therefore, this one does not exist. I'll just write DNE for does not exist. Okay, so for part G, they give us log base 2 of 20 minus log base 2 of 5. Here we observe that both logarithms have base 2, and there's subtraction between the two. And so we know we can kind of reverse what we did in part E, right? This would be equal to the first argument divided by the second argument. Of course, 20 divided by 5, that's equal 4. Log base 2. And I could write 4 here, but let's go ahead and just write it as 2 to the power of 2, right? That's a clever way of writing 4 to our benefit. And we could pull down the exponent. And then we see, okay, well, log base 2 of 2 is equal to 1. We've seen that before. And then we just get 2 times 1, which is equal to 2. Okay, on to question 19. We're asked to solve the following logarithmic equations to check our answers and write our final answer on the line. Okay, and so here, let's see, what should we do first, right? Right away, I guess we could assume here, right, or observe, right? If there's no base value, we can assume it's log base 10. And so if this is true, this logarithmic form, we know that this implies, right, an exponential form. So I'd probably convert this to exponential form first, right? And that means that since 10 is my base, it will be raised to 2, and this will be equal to 3x minus 5. Okay, so now I have access to my x, and I can solve for it. And so I'll start by probably just observing that 10 squared is equal to 100. and then I'll add 5 to both sides and have 3x remaining. And so here, I'll see that this implies that 100 plus 5 is 105, and divide by 3, that's my x value. Okay, so let's go ahead and we'll check our work, right? So let's see. I'm going to just say, well, what is this function, this logarithmic function, when I plug in, right, my x value that I just found, which is 105 over 3 minus 5. Okay, so right away, let's write my log. 3 times 105 over 3, we can see via simplification, that's equal 105, of course, minus 5. And then 105 minus 5, we know to be 100, which I could write 100 as 10 squared, right? Again, since there's no base stated, we assume it to be 10. And so we can use the property that we have log base 10 of 10, and we can pull down the 2, and so our output is 2. So there's our final answer. Okay, in part B, let's see, it's a little bit more complicated, isn't it? Okay, so right away, let's go ahead and apply the property. Since there's the same base of 3, and we're adding in between, we know we can combine those arguments, right, with multiplication. So I'll write the first argument times the second argument, and this is equal to. And so here, I would probably just go right away to exponent form, right? So it would be 3 is our base raised to the 2, right, is equal to x times 2x plus 3. Just like that. Now I have access to the x and I can solve. And so here, let's see, I'll have 9 is equal to 2x squared. So just doing a little bit of simplifying in the process, multiplying that x into the parentheses. And then subtracting 9 from both sides, I have that this implies that 2x squared plus 3x minus 9 is equal to 0. So a similar problem that I think we saw at the beginning of this review, in that we can apply whatever method you prefer. I'll just show, again, the IC method here. 2 times 9 is equal to 18. The factors of 18 that add up to be 3. Oh gosh, what are those? Let's see. Oh, and I'm sorry, this should be negative 9 technically, so negative 18. And so I think this will be negative 3 and 6, right? Because 3 times 6 is equal to 18. Negative 3 times 6 will be equal to negative 18. And of course, negative 3 plus 6 is equal to 3. So I can rewrite our equation with this new information. And I think I'll probably want to write it as plus 6x, right? Minus 3x minus 9, of course, equal to 0. Same song and dance. I'm going to factor out the GCF of the first 2 terms and find that I have x plus 3 after I factor out the 2x. And now looking at the next 2 terms, it'd probably be advantageous if I factor out a negative 3. You'll see why. The remaining will be x plus 3 after I pull out a negative 3 out of those 2 terms. Perfect. So I have an x plus 3 in both terms now, and so I can factor that out. And so I'll have 2x minus 3 times x plus 3 equals 0. And then solving this, we'll see that, well, this implies, right, because of the 0 product rule, that 2x minus 3 is equal to 0, or x plus 3 is equal to 0, right? So one thing to observe about this, right, if I say x plus 3 is equal to 0, that means that x is equal to negative 3, right? But notice that initially it's given that this expression, right, is log base 3 of x. And if I plug in -3 in there, then this is not inside the domain. Arguments can't be less than 0. So therefore, the only solution here, right, I'll say x cannot equal -3. So we'll see that if we solve this guy, we find that x is equal to 3/2, or 3/2. So I haven't left myself much room, but we want to check our work here. And so I probably would, let's see. Yeah, let's go ahead and see how would we do this, right? Log base 3 of 3/2, right? Plus log base 3 of 2 times 3/2 plus 3, right? Plugging in that x value. So right away, the second argument can be simplified, right? 2 times 3/2 is equal to 3, and 3 plus 3 is equal to 6. And then this, of course, is log base 3/2 times 6, right? Apologize, I dropped the 3. And so when we have, well, that's equal log base 3 of 9, right? Which log base 3 of 9 is equal to log base 3 of 3 squared, which is equal to 2. Okay, so moving on to part C, if I have enough room here, let's see. I have this expression. Let's see what this equation. What should we do initially here to start this one? I think here, again, I'd probably apply, since these are both the same base, assumed to be log base 10 here, since it's not stated. And so I would multiply the arguments right away. And so I can go ahead and do two things at once here, right? And distribute that to both of these, to 6x squared minus 7x is equal to log of 5, right? And so here, it's more of just an equality of arguments, right? If we have this to be true, it's the same basis, we see that it must be that 6x squared minus 7x is equal 5, right? And so here it's a similar story to what we just kind of saw, in that we have 6x squared minus 7x minus 5 equals 0. And I definitely have very little room to continue here. Let's see if I can create some room. Okay, moving over to a whiteboard, we see that we have this 6x squared minus 7x minus 5 set equal to 0. And so we can go ahead and just apply the AC method again, or you could use the quadratic formula. And so I'll have my A times my C, which is equal to -30. And then the two values that when the factors of -30 that sum to equal -7 would be 3 and -10. And so I can rewrite my 7x as plus 3x minus 10x minus 5 equaling 0. And going ahead and finding the GCF of the first two terms, it'll be, I believe, 3x times 2x plus 1. And then I think it'd be advantageous for me to factor out a -5. We'll see how that works. Okay, 2x plus 1 again. So that was good. Okay, so now I'm going to go ahead and factor out the 2x plus 1. Have this scenario. And so zero product rule says that either one of these must equal 0 for this to be a true statement. So the first one says that 3x minus 5 equals 0. And going ahead and solving for my x value, I find that x is equal to 5 over 3. And we also have the possibility that 2x plus 1 is equal to 0. And so we'll see, actually, as we go ahead and solve for x now, we fall into a little bit of trouble, right? Because we have to remember the original problem statement told us that it was log base 10 of 6x minus 7 plus the log base 10 of x. And so our argument can't be negative. So we can't have a negative 1/2 for our x. So this one over here does not work. So it means that this would be our x value of choice. And so we can check our results by go ahead and plugging in our log of 6 times 5 over 3. Oops. Go ahead and undo that trace. Okay, and then we had minus 7 plus the log of 5 over 3. Let's see what this equals. Right, so we have log, the first argument simplifies, right, to 2 times 5, which is equal 10 minus 7. Go ahead and keep the log of 5 over 3 over here for just a second. And then we see, okay, it would be 10 minus 7, which is equal to 3. And it would be 3. We'll go ahead and apply, since we have the same base here, and there's addition between these logarithms, we can multiply the arguments. And we'd find that, of course, this simplifies to log of 5, which is what we wanted. So perfect. Okay, moving on to the final question of the review. It's another story problem, and it tells us, they give us a function here, right? H of t. And in part A, they ask us to use it to find the height of the tree that is 5 years old, down to the nearest 1/10 of a foot. So here, I believe, right, we're just going to plug in, since t is equal to the age of a tree in years. We're going to ask ourselves, well, what is h of 5? So we just plug in 5 everywhere there is a t in our function, which is inside that natural log. And I think I used my calculator, obviously, to find this. And my calculator gave me something like 15. So move my decimal place here. 15.0799. Excuse me. And so here, I'd probably say something like, hey, after 5 years, the tree will be rounded to the nearest 10th, 15.1 feet tall. Something like that, right? Okay, in part B, they're asking us to use algebra to find the age of a tree that is 25 feet tall. And so noting that our function h of t gives us the height after t years, we're going to go ahead and just plug in, right, what the h of t function is equal to. I should say write down. It's supposed to be a 3 natural log, and the t value is the thing we want to find. And we're going to set this equal to 25. Okay, so next we're going to go ahead and just go after our t value, right? So to solve for our t value, we'll likely just start by subtracting 4.86 from both sides, and then we'll divide by 6.35. So I'll have the natural log of t on one side, and then again, we subtracted 4.86 from 25 divided by 6.35. Here it is advantageous. If we wanted to, we could go ahead and switch to exponential form, right? So this implies that E, right, our T value, I should say, is E raised to 25 minus 4.86 divided by 6.35. Perfect. Of course, using your calculator to find this would be the best scenario. And so I think this was approximately 23.84. And there were some more decimals beyond that. And they're asking us to round this to the nearest year. So I believe it would be T is equal to 24 years. You might take time to write that as a complete sentence for your final answer. For part C, we want to state the vertical asymptote and explain what it means in the context of this problem. And so, again, we're dealing with a logarithmic function. And so the vertical asymptote is where the argument is equal to 0. So here it would be t equaling 0 would be our vertical asymptote. And we would probably say something in the context of this situation that the age of the tree will always be greater than 0, right? Which is probably the best observation we could do here. You might come up with another idea, but that's possibly what I would do there. And so for part D, it's asking us, is it reasonable to assume this logarithmic model will continue indefinitely? And if so, or if not, why or why not? So you could come up with some ideas of what would happen here in this scenario, right? We're talking about the growth of a tree. I think it's likely, obviously, we all kind of come to the same conclusion that it's not reasonable. It is not reasonable, right? And some of your thoughts might be, trees eventually die. And I think that would probably be the best, right? Eventually die. They get sick, they get cut down, whatever it is. Okay, that's the review session. Thanks for watching.